Welcome to Alplakes. Alplakes is an ESA-funded research project that provides monitoring and forecasting for the state of lakes across the European alpine region, utilizing operational hydrodynamic models and remote sensing data. This video will cover some of the functionality of Alplakes and provide an overview of the software architecture that runs behind the scenes. But first, an introduction to the Alplakes website. The homepage of the Alplakes website provides a list of selected lakes from across the alpine region. Each lake has a 4 to 5 day forecast of average water temperature and displays a number of key parameters such as elevation, depth, and surface area. The list can be sorted by each of these parameters. Users can select their desired lake and are directed to the lake interface. The lake interface is constructed from a number of components. The data viewer provides an animated overview of the forecasted lake conditions. The data viewer is an interactive video player, meaning you can zoom in on a given region during the animation. As with a video player, you can pause and unpause the animation. You can use the slider to select a specific time point within the period, and you can use the next button to process slowly through the time steps. The settings allow you to control the step interval, playback speed, and alter the base map, for example, to aerial imagery. It's also possible to expand to full screen. Next, we look at the depth data selector. Here you can select from a number of depths. In this example, we pick 31 meters. This then collects the data from the API for this depth. You can see in the above graph that the water temperature is much cooler down at 30 meters, and we'll go back to the surface temperature for the remainder of this exercise. Using the calendar, you can select a specific time period from the past. You can select longer periods, shorter periods. For example, we'll select a couple of days. In the layer settings, you can adjust the visualization of each layer. Here we're adjusting the settings for the current. We can turn off the arrow visualization and turn on streamlines. We can change the speed of the streamlines, and it alters the visualization. We can add a raster layer, which gives us an indication of the intensity of the current in different places, and when combined with the arrows, can give us insights into the state of the lake. For the temperature, we could adjust the palette. This allows people to customize the visualization to get the most from it that they need. We can also add additional layers. There's a number to select from. For example, thermocline depth. This is calculated from the simulation results and is available at 3-hour time steps. This is calculated using an open source Python package called PyLake. The user can take interactive transects of the lake. You first draw the line. The request is then sent to the server. And when the result comes back, you can interact with the heat map that comes up. We can do something similar for profiles. Again, we have an interactive interface to select the profile location, sends it to the server, and we get back a heat map. An interesting feature here is we can look at the profiles across time and across depth layers and see in more detail the variations that are occurring. In order to better understand how things move around the lake, we have an inbuilt particle tracker. A user can select where they want to add particles in the lake, and then we go back to the video controls to see how those particles move around the lake based on the currents from the simulation. It's also possible to overlay satellite imagery onto the data viewer. In this case, we're looking at Sentinel-3. We can add the chlorophyll. The calendar shows where data is available, and the amount of shading in the box indicates the number of pixels available to view. And the user can easily select between the different available layers. We also have Sentinel-2 layers. As you'll see from the calendar, the return time of the satellite is less. However, the resolution is much higher. If we're interested in seeing the raw data behind where the satellite images come from, we can plot the RGB returns from the satellite. Here we can remove the temperature and adjust the opacity of the Sentinel-2 product. And we can see how the RGB image relates to the product that we see.